Hello AP Statistics students. In this video, we're going to be calculating the standard deviation of a discrete random variable. Now, in our calculation for the standard deviation, we are also going to be looking at something called the variance. Don't worry, that is simply an intermediate step to finding the standard deviation. If you remember, the standard deviation's got a decently long calculation, but it's similar but not as bad as it used to be for a discrete random variable. Then we're going to move on from a discrete random variable to a continuous random variable. Thankfully, those are going to be nice and easy because we've done this concept before. It's something that we've already looked at. So that'll be nice and easy. All right, so first, the standard deviation. So just a quick reminder what the standard deviation measures for us. Of a discrete random variable, the standard deviation measures how much the values of the variable, and here's the big thing, typically vary from the mean in many, many trials. All right, in many, many random iterations, how far do the values of your random variable typically vary from the mean? Hopefully that sets up our sentence frame to something we're very used to writing. All right, now here is the formula for standard deviation for a discrete random variable. All right, it might look kind of crazy at first, but let's break it down. All right, first, we have the Greek letter S here for standard deviation. This is not a sample, so we are using the Greek letter here. All right, again, summation, the capital S in Greek here is simply means to add up or to sum. This right here is those are our individual data points. All right, mu, again, we're using Greek letters. The Greek letter M for mu, that is the mean. So there we are subtracting the mean from each data point. From each value of x, we are subtracting the mean. We're finding the difference, the distance, essentially. But remember, we square it to get rid of the negatives. Now here's the one difference with the discrete random variables over other data sets. Other data sets we usually divided by n-1, if you remember, to find an average. This time, we multiply by the probability. If you remember, each question has a probability distribution. That's that table that has all the probabilities. We simply multiply by the probability instead of dividing by n-1. It accomplishes very much the same thing. All right, so that's how we're going to calculate. That's what all the pieces of the formula are. Now, the variance, that is the stuff inside the square root. Okay, so the variance is equal to just the sum of x sub I minus mu sub x squared times the probability of each individual x. Now, we oftentimes write this as sigma squared. Okay, because it doesn't have the square root. Imagine squaring both sides. That would get rid of the square root, and that would leave just the stuff that was on the inside. So the variance is oftentimes where you start. You calculate the insides. That is sigma squared, the variance. And then if you want the actual standard deviation, you just square root the variance. All right, so the standard deviation is equal to the square root of the variance, which is sigma squared. That sounds a little redundant, I know, because the square root and the square just cancel out. All right, that's enough theory there. Let's actually do a problem. We're going to use our APGAR scores example again. So remember, when a baby is born, it is given an APGAR score from 0 to 10 based off of 5 different criteria. The baby can score 0, 1, or a 2 for each criteria, which makes a total of 10 possible points. So here is our probability distribution for APGAR scores. We're going to calculate the standard deviation of APGAR scores. Now remember, in class we already found the expected value, or the average APGAR score is 8.128. Remember, you simply multiply each value of x times its probability, and then you add them all together. That gives you your average. But we did that already. It's 8.128. So now it's time to calculate the variance. All right, this is sigma squared. We will square root this to find the standard deviation at the end, but this is an intermediate step. So the variance is just the inside of the formula. So what we do is we take each x value, we subtract off the average, we square it, then we multiply by the probability, and we have to add them all together. So for the first one here, we're going to take a score of 0, subtract the average from it, 8.128, multiply by its probability, which is 0.001. Then we do the next for the next value. All right, so now we're going to take an APGAR score of 1, subtract the average, square it to get rid of negatives, multiply by the probability of this one, which is 0.006. Now, as you can see, this is quite tedious. I'm going to do one more, and then I'm going to pause my video, and all the answers will appear. Maybe you can pause your video and try to fill out the rest of these without me. So the next one, I take 2 minus the average, 8.128, square it, multiply by the probability, which is 0.007. All right. Pause the video here, see if you can fill out the rest. I'm going to do the same, and so the answers are going to appear there in just a second. And voila, there is the entire formula there. Check yours, make sure you get it. When you hit enter, you should get a variance here of 2.066. All right, now that is the intermediate step. We just did everything inside the square root. So if we actually want the standard deviation, we have to square root that number. So the square root of 2.066 is 1.44-ish, if you round up there. That is our standard deviation. So again, what the heck does that number now mean? All right, if we select many babies at random, their APGAR score will typically vary by 1.44 units away from the mean, of 8.128. All right, they will typically be about 1.44 units away from the average of 1.128. All right, so that's a big, long calculation. That's about as tedious as we will ever get there. Let's do a shorter one to see this one more time, all right? So back to our life insurance policy question. So a life insurance company pays policyholders 10 grand in case of death, 5,000 in case of disability. An actuary determines the probability distribution for the random variable X, which is the amount paid to each policy. All right, essentially the death rate and the disability rate for these outcomes. All right, so first, if we're going to do this, I don't have the average value, so I do need the average or the expected value of X. Remember, that is the same as the average value, the mean of X. So we simply multiply each of these together, the value of X times its probability, the value of X times its probability, the value of X times its probability, and we add them together. So I'm going to do that real quick. 10,000, 001 plus 5,000 times 0.002 I could add the third one, but it's just multiplying by 0, so it doesn't matter. Our average value there is 20. So on average, we're paying out $20 to each person. Now that's an average, right? We're not actually paying each person 20 bucks. Most people are getting 0. A few people are getting much higher numbers, but on average, it's 20. So if I want the standard deviation here, first I'm going to find the variance, all right? I want us to get used to using the word variance, talking about variance, because it does become quite important later on. So we take the first value, 10,000, subtract off the mean, square it, multiply by its probability, plus 5,000 minus the mean, square it, multiply by the probability. And last, $0 minus the mean, square it, multiply by its probability. All right. Then type that into your calculator to finish off getting the variance. All right. Make sure you can type that into the calculator. Make sure you can see how to use all those parentheses, etc. Be careful with them. There's a lot of places to make mistakes. But we get a variance, a sigma squared of 149,600. If we want the standard deviation, we just square root that, and we get 386.78. So what does the standard deviation mean? All right. If you have many policies, the amount paid out will typically vary by $386.78 away from the mean of $20. All right, that one has quite the big spread, doesn't it? That is a very big number because, well, our values of x are very spread out. Most people are getting 0, but some people are getting 5,000, and a few people are even getting $10,000. They're very spread out. We have a higher standard deviation. All right, hopefully this sentence makes sense, and hopefully you can see how to calculate that standard deviation from a probability distribution. It's a little tedious, but you're not going to have to do that for very big data sets usually. All right, moving on. Continuous random variables. So moving away from a discrete variable where x has certain discrete values. So there, x only had 3 values that it could take on: 10,000, 5,000, 0. But what about a continuous random variable where x could take on any number? It's in a continuum now, which, pretty good show, by the way. I'm a sci-fi fan. Look it up on Netflix. So what do we do when we have a continuous random variable where x could be any number? Well, the main thing is our probability distribution is no longer a table, okay? We can't use a table for our probability distribution, all right? Because x can take on any number, we can't put every single number there is in a table. That just won't work. So instead, we will use a probability density function. Now that should sound a little familiar to you. We've done probability density functions before. That's what the normal model is. The normal model is a probability density function, which is why this is not going to be that hard. We've done this, okay? I think we've actually done this exact problem before, but now we're doing it in the lens of random variables. So Selena works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway that would allow her to get from the main terminal to the bookstore in just 4 minutes. She wonders if it will be faster to walk or take the train to work. Let all right, so here's our random variable. Let y equal Selena's journey time to work by train on a randomly selected day. The probability distribution, here we go, of y can be modeled by a uniform density curve on the interval from 2 to 5. Find the probability that it will be quicker for Selena to take the train than to walk on a given random day. All right, so a little hard here. So first we're going to take a look at the train. And we're going to compare that to walking. So walking apparently had no variability. Walking, it was always going to take her 4 minutes. All right, no traffic when you're walking on this special walkway, so it's always 4 minutes, no variability. But for the train, there was variability. Okay, and we can model that variability using a probability distribution of a uniform density curve from 2 to 5. All right, so a uniform density curve from 2 to 5. So we start here at 2, and we go up here to 5. It's uniform, so this is going to simply be a rectangle. It's not a normal model, it's just a rectangle. Wow, if I could draw straight, that would be awesome. That's supposed to be a horizontal line. Bear with me, okay? So here is our uniform probability model, our uniform density curve. How tall is it though? Okay, how tall is this? Well, we do need to remember that the area here, the total area, is always equal to 1. All right, the total area is always equal to, because the probability of her getting to work is 100%. Okay, any probability distribution has to equal 100%. So we go 2, 3, 4, 5. All right, if we have 3 units along the bottom, this is basically just length times width, right? How tall does this have to be? It needs to be 1/3 tall. All right, 1/3 tall. Now, we've got our probability distribution over here. Maybe I should label that probability distribution. So instead of a table, we have our graph here. All right, so this is what we have instead of a table. We have this density curve. All right, but we want to compare it with walking. How often is walking faster? How often is taking the train faster? Well, the train is faster right here. Whenever it's less than 4. So what is that probability? The probability of our random variable y being less than 4 is equal to, well, it's the area of that new rectangle. Has a base of 2 times a height of 1/3. So that is 2/3. Or 2 divided by 3 is about 67%. So 67% of the time, or there is a 67% chance on a random day the train will be faster. Than walking. I'm hoping that looks kind of familiar because we've done this before, just not in the lens of probability of random variables. All right, last one here, ladies and gentlemen. Now we're going to use the normal distribution curve. So the heights of young women can be modeled by a normal distribution with mean of 64 inches and a standard deviation of 2.7 inches. Suppose we choose a young woman at random and let y, here's our random variable, equal her height in inches. Find the probability that y is between 68 and 70. Well, so here's our probability distribution. It's a normal curve. That is a horrible normal curve, but I'm going to go with it. All right, don't judge me. So the mean is 64, and the standard deviation is 2.7. So we're going to add 2.7, and we're going to subtract 2.7 both directions. So that will be 66.7, etc. Let's see, 432, 61.3, going that direction. And you can continue to add and subtract if you like. We want to find the probability we are between 68 and 70. So somewhere up here is 68, and somewhere over here is 70. We want to find this area right here. And that should look real familiar to you. That is simply a normal CDF. It's been a while since we've done a normal CDF, right? But should be like riding a bike here. So normal CDF, where our mean is 64, our standard deviation is 2.7, and our lower is 68, and our upper is 70. Now, everybody's calculator is a little bit different for plugging that in, so be careful on the order for what you plug. I think that's the order for the TI-84s, but if you have a different calculator, it might be a different order. Just be careful when you type it in. Make sure you get everything in the right place. But that will give you the probability of that happening for a random woman. Hopefully that looks familiar, because that should be like riding an old bike, don't you think? All right, ladies and gentlemen, good luck with that.